All right, we're recording. Everybody shut up. Online people, make sure you get your cameras on if you have one. I know, Will, you're not on one that has one, but otherwise the face recognition thing that they added won't count you here, and then the provost will scream at you, and that's not my problem. So it is what it is. Okay. Oh, interesting first world problem last night. So coming back from had dinner with a former master student from here from like 7 years ago. We met up in Milwaukee. So I'm coming home from there. And you know how cars, modern cars, have like, the sensors for the windshield wipers, whether or not they'll turn on or not, like based on whether there's moisture. Well, it's detecting the ice on my windshield as moisture. So it's just dragging ice back and forth across the, it's like, okay, you want to turn that off. Okay, well, I drive a Tesla, so I want my car to drive myself. I don't want to have to, I shouldn't have to drive my car, right? Like, that's overrated. So I wanted to drive me home. But if you have autopilot on, you can't turn off the windshield wipers. You got to choose. I have to choose between the car drive me and have ice scraping back and forth, or me drive with no ice scraping. Huh? I know. I started thinking to myself, I was like, man, this is like all sorts of levels of pathetic. That this is now like a problem. I chose the car drive itself. Because it did let me set it to like the slowest. I could change the rate at which the windshield wipers would go. And I determined, since the sensors were going nuts, that the slowest windshield wiper was better than the auto. Because auto thought I was in a torrential downpour, I think. It was just going back and forth. So it is really a first world problem. It's terrible.
So
Yeah.
So with that, do you just put the like directions you want it, or does it have to be a straight drive?
No, you put in it depends which version of the software you have. I have the full self-driving beta, so you just put in the GPS location and turn it on, and it takes you there. It won't pull into my driveway, but it'll basically stop right outside my house. Yeah.
So does it like know to stop at
Oh yeah. Yeah.
I would hope it does.
No. Everybody just gets out of the way. It honks. It does a lot of honking. Yeah, it's a way better way of handling an intersection between Port Washington to where Meyer is, because that's like a blind turn. Yeah, it doesn't even look. Just lays on it around the curve. It does sometimes act funny though. Like, I don't think you'd hit something, but like sometimes it'll like take a turn, and then it'll like correct the wrong direction and overcorrect and like freak other cars out.
So does it know, like, if you come to a stop sign, usually after you stop, you go right away, but does it know if there's other cars at the intersection?
Oh yeah, it sees like everything all around it. Yeah, it's insane. But I have reprogrammed my horn to be the La Cucaracha song, so I can just hit it. So yeah, it's problematic. But yeah, I was very disappointed in that windshield wiper situation. I'll probably, well, I shouldn't have to do that either. I'll have to find a grad student, go get the ice off the windshield wipers. No, the way to do it is you got to go through the Better Business Bureau. Yeah, you never go to the company directly. If you ever need something accomplished, you go through the Better Business Bureau. I'll tell you what, it takes like 2 seconds. I'm not saying abuse it, but it takes like 2 seconds to put in, well, realistically, it probably takes 3 minutes to put in a complaint about something, and it almost always gets resolved within 3 or 4 days. So let's say you have like a complaint on your cell phone bill. You got charged for something weird, whatever. Don't call and be on hold with them and have to negotiate with the customer service person, who's might be plenty nice, but they don't have the button, right? They don't have the magical button that'll fix your problem. Just submit a claim through the Better Business Bureau, bbb.org. And because I did this after my trip, I got charged for all these international things when I was on Wi-Fi calling. It's like $700. So I put in a complaint. Next day, I'm getting a call from some lady in the president's office at AT&T. It's like, well, I'll call you back on Monday once the bill actually processes, so I know exactly how much money we're giving you back. And then they just added 20% onto it, for my trouble. First world problems. But that's not as bad as the windshield wiper situation. It's uncalled for. Okay. So now that we've covered unrelated stuff, but life hacks, let's get back to our let's see, am I sharing? I am sharing my screen. Am I recording? I am recording. Okay, so let's keep cooking here. So last time we basically learned 85% of the Java programming language based on what we had learned last semester. So we're gonna kind of finish doing that transition today. So we did talk about, kind of Java compared to C++, platform independent, runs on the Java virtual machine. It's a compiled language. Then we started to, as we did these 3 slides, basically take us through the transition. So how do human beings solve problems? Memory, asking questions, repetition. We have our mapping of 100% of programming languages will give us facilities for representing memory, done through variables, asking questions, done through conditionals, and repetition, done through loops and functions. Pretty quickly here, we see that the way we accomplish all 3 of these things in Java is extremely similar to how we accomplish that in C++, right? We go back to our code here. Here I'm defining a variable that looks just like I would do if I was defining a variable named A in C++ and setting it equal to 5, it would be identical, right? Okay, a for loop looks the same. If I were to write a while loop, looks the same. So really out of the stuff we're looking at here, the only thing that's really changed is how do I write something out to the screen? I say system.out.println instead of cout, which we looked at last semester. So if we start kind of collecting stuff. So system.out.println. Actually, let's do this as separate slides, maybe. Write to screen. We have system.out.println. We also have system.out.print. Displays the string to the screen and presses return. Does the same, but does not press return. So whether you put the ln on that or not dictates whether or not you tell it to kick down a line. So if I back up here, so if I do system.out.print hello world, that's not going to press enter at the end of it. So it's not going to kick it down the line. Then if I print out woot, it's going to put it right at the end of that same line. So there's the hello world woot. If I change this to an ln, it'll press enter at the end of that guy. Now woot will be on its own line. I could avoid using ln and instead maybe our equivalent to end L from last semester is just throwing a \n. The end of it that just says line feed is what the placeholder is. So that'll kick it down a line as well. Okay, so that's displaying stuff to the screen. We saw a function last time. For right now, I said always just put static out front. We'll start talking about that here pretty soon. Name of this is our return type, same as last semester. The name of the function, add nums. same as last semester, open parenthesis, parameter list. Every parameter has a type and then a name. Same as last semester. So this guy is going to take in, it's called addnoms, is going to take in 2 integers and return an integer. So this guy's going to return those 2 values added together, whatever I pass in. Okay, so if I say I want to print out addnoms 1 and 2, I'll get a 3 out of that, right? And if I do 5 and 7, I'll get a 12 out of that. So I'm calling the same function 2 different times, passing it different inputs, getting different outputs. So far, nothing different compared to Java versus C++. Okay, so highly, highly related to each other because they're both based on, I guess, the C programming language. All right. Now, one thing that would be different, though. Just going to take this function. I'm going to put it after main. If we were in C++, what would I have to do here? I'd have to prototype it. Okay, so in C++, in order for me to use a function inside of main, that function needed to be previously defined. So if I was in C++, I would have had to do this. I would have had to at least do a one-liner up there, letting the compiler know, hey, there is going to be this thing called addnoms that takes 2 integers and returns an int. I'm going to implement it later, but trust me, he'll be there. C++ will make you prototype it. Java does not. Java uses what's called a 2-pass compiler. And most modern C++ compilers are capable of 2-pass. You just have to pass it a flag to make it work that way. But Java is perfectly happy doing this. It's like, look, you give us the function, I'll find it, and there's my output. All right, so you need to maybe pay a little bit less attention of the order you put things in. Kind of maybe a nicety for us when you decide, okay, I have this function that's going to call this function, but this function calls this function. What the heck do I do? That's when you had to prototype them and then actually implement them later on. Now Java will just figure it out. That seems like kind of a stupid thing for a programmer to have to maybe waste their time trying to figure out, right? That's a nicety of Java. Java solves that problem for us. Okay. Generally speaking, I would say I always put main up top and then I write my other functions down on the bottom, following that idea that all programs begin and end with main. So I like to see main first and then all my helpers are down on the bottom. Go ahead. To be honest, I'm not sure if there's like a global best practice because you will just as commonly find people write their functions first and then have main later on. So I would say no, but maybe just be consistent. But actually, let's take that a little bit one step further. Most companies you might go and work for, they, as part of your training, they'll take you through their own best practices. So they'll kind of dictate to you, this is how we do things here. And whether you agree with it or not, like for instance, I'm kind of a stickler for the curly braces being left justified, like this, where almost every IDE these days would write it like that. And that really came from a long time ago when books wanted to save a line for the printing press to get it in there. Well, this just became kind of standard practice. Now, what's funny is I was programming back then, but I still just prefer this look. You see where the function begins, you see where it ends, everything in between, that's the meat of the sandwich. Okay, that's what goes in there. So I tend to really like this syntax for it, but you might go and work for a company that says our way of writing this is that. And they expect you to write it that way, even though the compiler doesn't care. That just comes down to coding conventions, that kind of stuff. All right, so there's functions in there. So now let's look at some string stuff. So we kind of have our fundamentals now, right? We can define some variables, we can write some loops, we can ask some questions, we can write a couple of functions and do something with those functions. But now we got to start increasing the types that we're used to working with. So if we think back to last semester, the types we dealt with, so C++, actually let's call these guys Java primitive types. We have byte, short. I want these to not get capitalized if possible. Int, long, char, float, double, and Boolean. So these should look very, 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 very familiar, with the little exception being that Boolean is spelled out in Java, where in C++ it was bool. I think actually in all caps, right? I don't remember, but same thing, same types, right? Right. Other things are still true. A byte is 8-bit signed integer. (16-bit) signed integer, 32-bit signed integer, 64-bit signed integer. So all these are the same for int types, right? So this is -127 or -128 to +127. This is -32,768 to +32,767. This is ±2.1 billion. And this is plus or minus big number, like 9.6 quadrillion or something like that. So this 2 to the 63rd, plus or minus that. And there's your 2.1 billion for ints, plus or minus that. And there's your shorts, plus or minus that. All right, because these are all signed, like it hold positive and negative numbers. No difference to what we ran into in C++. So again, we go back to a historical programmer where we don't have a lot of memory in our computers. We should be good stewards of our memory. And if you only need to hold numbers between 1 and 10, or numbers that'll fit between -258 and +257. I'm sorry, -128 and +127. If all the numbers you're working with fit in there, you should use a byte because that's the most memory efficient. Okay. If you're only going to hold numbers between -32,768 and +32,767, you should use a short because only be memory efficient. What's the reality? The reality is our modern programmer, they use an int. If you want to hold a whole number, positive and negative, you use an int. If that's not big enough, you use a long. If that's not big enough, now we got to dive over to the object side. And like in Java, we would use something like big integer. We have a class that allows you to just have arbitrary size numbers at the cost of speed. All right. So the modern programmer is less concerned about memory because we got a bunch of memory. All right. I mean, we remember from last semester, he had 128 gigabytes. Have you upped that yet? Or you're still sitting at 128? Static. I mean, it's been 2.5 months. Yeah. So I mean, this is worse than the Tesla problem. He's just gonna get a server with 2 terabytes of RAM, and he'll claim he's going to use it. Well, maybe he will. He just write an infinite loop with lots of recursive calls. fill it up quick. Okay, but bottom line is, even those of us in here with, unless you have a really, really old, computer, where it's like, look, this is like not as good as your toaster. You're kind of bragging about it like this thing's been through wars. Even your most relatively budget pleaser computer today Maybe it comes with 8 gigabytes. Maybe your computer has 4 gigabytes of RAM. That's still plenty where you don't have to worry about whether or not to use an int or a short or a byte. Okay. But these are all signed numbers, just like in C++. Signed means can hold positive and negative numbers. Now here's a little difference. If you remember, char in C++ was an 8-bit unsigned number. So that's 0 to 255 in C++. And that was because it mapped to the ASCII character set. Okay, so like an A is a certain number, a B is another number, so on and so forth. Java uses the Unicode character set. So in Java, a char actually is a 16-bit unsigned integer. So 0 to 65,535. So there are 65,536 unique characters in the Unicode character set, kind of covering a bunch of different languages and symbols and things like that. But again, from our perspective as a modern programmer, if you want to store a character, you put it in a char. Unicode's the number for a letter A in Unicode, which is what, a 65? Or is that an uppercase A? I think a lowercase a is 65 and uppercase a is a 97. That might be flipped. Something like that. Give me a moment. One of these is going to be 65, I think. The other one would be 97. Okay. 65 and 97. So lowercase a is 97, uppercase a is 65. If we were to do that same thing in C++, we'd get the same numbers. So Unicode, the Unicode character set is a superset of ASCII. The first 256 characters are the same. Actually, original ASCII was only 128 characters, but you had more bits to work with, so they just filled that in with like playing cards and smiley faces and crap like that. Isn't that kind of funny? You go back then and it's like, okay, well, because it was very much, it's the American Standard Code for Information Interchange is what ASCII stands for. It's like, well, we only came up with 128 symbols that we want to represent. So, we have 128 more to work with. Should we support other languages? No. Let's put smiley faces and stuff. It's just kind of funny. Things never change. All right. But Unicode is just a larger character set, supports multiple natural languages around the world, and at the cost of having to use a little bit larger data type to represent that many unique characters. And why do we need this mapping? Because computers like numbers, right? Computers are good at storing numbers. But ultimately, human beings, we want, we don't want to just see if we had hello world spit out to the screen. So if I go back here, actually, I'll just write it this way. We're going to be introducing strings in a second anyways. So we'll say hello world. And then I write a loop for int I is equal to 0. I is less than s dot length. That's the length of a string in Java. I plus plus. And then I would say system.out.print int of s dot char at I. That's not very meaningful to us, even if I put a little space after it. That'll separate the. So to a human being, we look at this. This is hello world. This is the number that if you were to take it to the Unicode character set, and I went to number 104, I'd find an H. I went to 101, I'd find an E. I went to 108, I'd find an L. Another 108, so on and so forth. Okay, it would map all those to give me hello world. Okay, but we don't want to have to do that. That ability is built into the language. It'll map it for us. So there's our hello world. Make sense? Computers like storing numbers. At some point, we want to see those guys as letters. If we're working with chars, there has to be a lookup table to do that mapping. No difference with Java than with C++, other than Java supports an expanded character set called Unicode, as do pretty much all of our modern programming languages. Okay, so now that we've going with this, so that's a char. Float is 32-bit signed integer before decimal, 16-bit unsigned after decimal. A double is 64-bit and 32-bit. So this is a total of 48 bits. And this is a total of 96 bits. And then a Boolean is a 8-bit unsigned integer. So basically a byte, because that's the smallest type we have in the language. But really it only needs 1 bit, a 0 or a 1. It's just the best way to represent that. The smallest way to represent that in the language is with 8 bits. But in Java or C++, you could technically do math with Booleans. Java, you cannot. Java doesn't let you pull the trues and falses out, turn them into 0s and 1s. Yeah. It probably does. I'm guessing it, well, no, because I doubt it stores a decimal point. It probably just reads the first 32 bits. Yeah, and then when it displays it, it puts the decimal point there. So it would take up memory in something called the frame buffer when it's actually displaying it, but in terms of storing it, it'll just store the first 32 bits mean the stuff before the decimal point. The next 16 bits you bump into in your computer storage means the stuff that's going to come after it. So when you actually display it to the screen, it'll just make sure it sticks the decimal point in the right place. All right, so those are our Java primitive types. Mostly identical to C++. And for all practical purposes, from our perspective, identical to C++, because we're only actually seeing some of these variances if we try to do kind of under the hood stuff, right? This is not going to be a super common thing. We're not going to commonly say, I want to force this character to turn into an int. We can do it, but that's not necessarily something we would do all the time, right? Go ahead.
What specific reason would you like ever need to use that for?
Okay. So there are practical reasons. Did we talk about Caesar Cipher last semester? This is just one example. But and we'll write it because it'll let us practice some of the stuff. So we'll just do some stuff by example. I think that's how it's spelled. Caesar cipher. Sometimes it's called ROT13. So we talk about these are encryption algorithms, taking something that is readable, turning it into something that's less readable, than being able to turn it back. All right. So modernly, we have to have these guys be pretty, pretty beefy, using various RSA or other kinds of encryption algorithms, because we have computers that can crack it, right? But way back when you didn't have the computers, and maybe you didn't have the time, and how long does the message actually need to be safe? I'm pretty sure that the crackerjack decoder rings were based on ROT13. Pretty sure about that. But so the way ROT13 works is to encrypt, we take each character and add 13 to it, wrapping the alphabet. So let me just do something here real quick. This is another little handy thing you can do with programming. So I'm going to say so there's our alphabet. I'm going to go through all the letters of the alphabet, and what I'm going to do is on the first line, I'm going to do a system dot out dot println I. I'll actually say print I. I'm going to do the same loop again. I'm actually going to print out s.charat I. This gives me, oh, I need to do a println. Oh, it's not going to space it good. Oh, it's because I have, let me do. I wrapped it on the screen though, but it did line them up. I guess I can try to copy all that. Let's see what that looks like. Yeah, it's still not spaced great, but you get the point here. We could map it out a little bit, but I got my mapping now. So an H is a number 7. We add 13. So hello world. We'll just do all lowercase. Actually, let's just do hello. It'll be quicker. Okay, so hello is number 7. 7 plus 13 is 20. So we'll go to number 20. 12, 13, 14, 15, 16, 17, 18, 19, 20 is a V. That's going to be a V. And E is, we need to go to a 17. 12, 13, 14, 15, 16, 17 is an S. L is a I think I'm already off because of my spacing here. It's happened before, but you get the point. We add 13 to the number and we give you that character underneath, and we'll write the code to give you the correct thing. Oh, you know what? This will work. Let's just do s.char at I concatenated with open parenthesis I close parenthesis. Let me just do an extra space there at the end. That'll have a better space between all of them. All right. So hello, we find our H in here. That's a 7. Add 13 to it. That's going to get us to a 20. A 20 is a U. And E is a 4 plus 13 is a 17. That's an R. And L is a 10 plus 13 is a 23. So that is an X. And then an O is a 14 plus 13 is a 27. Okay, so we see that 27 takes us off the end. So we wrap around. That's 25, 26, 27. So that's a B. So that is the encoded version of hello. Now, what's interesting here is if I take a U, which is a 20, and I add 13 to it, I'm going to get a 33, right? 33, we're going to do the mod. That gives us a remainder from 26. 33 gives us a remainder of 7. So this is going to map back to an H. R, 17 plus 13 is 30. 30 mod 26 is a remainder of 4. That's an E. X is 23. 23 plus 13 is 36. 36 mod 26 is a 10. No, it's a 33. Oh, I made a mistake the first way around. All right. But in any case, it wraps back around. So that thing will, so it's actually a it's not an X, it's a what? Y. And that guy will, so using the same exact algorithm, we can encode and decode. So we'll see, actually writing the program for this is easier. So if we just write a function, static let's do rot 13. And we have this guy take in a char as a parameter. Now we might say we want to use the alphabet here to do it. You could actually just take advantage, and I'll show you in a second. You can take advantage of how Unicode works. All right, so there's our alphabet. We need to find the location in this string where this character exists. There is a function for doing that, but let's just go ahead and write the logic. So we'll say for int I is equal to 0, I is less than s dot length I plus plus. So effectively, the problem we're solving right now is, given this string, tell us the position where this character lives. In fact, we could even put that into a little function. So static int find index of, have that guy taken a, we'll just solve small problems. So I want to go through every character of that string and say, is the character I'm currently looking at equal to the character you asked me to find? If it is, I'll return the current index. Now, just like in C++, I have advertised that I will be returning an integer. So there is no guarantee that we will ever, from Java's perspective, there's no guarantee we will ever get into that if statement. So at the very end here, if I never find it, I'll return a -1. So now I have something called find index of, a function called find index of. Make that void for a second here. I'll come back to that. So now up here, I can do something like system.out.println find index of an H. And this will tell me where in the alphabet that H occurred. So it's at a 7 and H was at a 7. Okay, so find index of this function right here, it just solves the little problem of, I will give you a character. Presumably, I'm going to give you a letter of the alphabet that's lowercase. And I will tell you where in this string I found that. Or a -1 if I never found it. That's all that function does. We ran over to Home Depot. We bought this little tiny widget on sale, $1.99. I can drop a character into it. It'll spit out where in the alphabet that character is. Make sense? We haven't solved the whole ROT13 problem yet. We just solved that one little piece. So now ROT13, so I'm going to take in a character. I want to find out where that character lives. So int start pause is equal to find index of C, which is going to be a number, right? That's going to give me the number in the alphabet where that guy lives. Then I have my alphabet there. Actually, I don't even need the alphabet in here. I'll use them in here. So I'm going to say npos is equal to start pause plus 13. So that's going to give me a number, right? But that number might be larger than 25, 0 to the end of the alphabet. So I need to mod that by 26. That'll wrap it back around. And then I'll return s.charat npos. So ROT13 will take a single character and map it to 13 characters forward wrapping. Now I can go up here. There's my hello. I'll run through that. And for each character, I'll do a print ROT13 on s.charat I. So this will convert hello to its ROT13 equivalent. Where didn't I put this? 1, 2, 3. Oh, there we go. Oh, I had ROT13 set up as void. I'm returning a character, so it's going to return a char. So there is hello encoded. But if I wanted to, I can decode it too. So just in our last couple minutes, I can say string answer starts off as the empty string. And what I'll do is I'll say answer is equal to answer concatenated with this guy. So I'll just build up my converted characters inside of the string called answer, just like we would have done in C++. And I'll output my final answer. That way I have my encoded version later on. All right. So now I'm going to go through all the characters of my answer. There, we'll just say string decoded. Starts off as the empty string. I'll just steal this line. So decoded. I'm going to go through all the characters in the answer, which is my encrypted Rsa encrypted version of my string, and decrypt it by encrypting it again. Rsa is exactly half the size of the alphabet, so they'll encrypt and decrypt using the same function. And I should get my hello back. So there's hello decrypted. So there's an example where we might decide to use the numbers of things. Now, in this case, we're doing it based on the alphabet, but we could do it based on the entire Unicode character set if we wanted to, right? We just take 65,536 becomes our 26, and we can encrypt anything in the Unicode character set using that same thing. All right. So sometimes the numerical version of something, in this case, I'm faking the numerical version using my lookup, find index of, but we could also just grab the int version of it from the Unicode character set, get a 97 for a lowercase a, add 13 to that is going to give us 110. And number 110, show you a quick system.out.println, the char version of 110. H, what did I say? H? Oh, because that's off an A. So A to N is 13 spaces, right? So if I started off with the char A, I get that. I could also actually say this, system.out.println A plus 13. Well, it wants me to turn that into a char real quick. I know we're out of time. So just finish this real quick. There's my 110. And then I can say, give me the char version of all that. And that'll convert it back to a char. So you can do math with it as well. Again, you asked the question. Not necessarily overly practical or something you would do all the time, but it's something that can be done, and it can be done because of how it's numerically organized in that lookup table. All right. So I'll take your question here in a second, but that's it for today. No homework for Friday, but make sure you're kind of following along, practicing this stuff, kind of converting your C++ knowledge to Java. And I'll see everybody on Friday, but I'll take your question. I'll leave the recording going. What's up?
So you mentioned this is like, I guess, like not primitive, but like I guess old school type of thing. So how did they like, I guess, develop this into something more advanced than what else did they do?
Well, what do you mean?
Because you said this is like, I guess, this was like the beginning of it, so it wasn't like that.
Oh, like the Caesar cipher, the ROT13 thing? Well, yeah, because I mean that's not that secure, right? That's why I was saying it's the back thing for the Cracker Jack box decoder ring. You know, you just turn it and it gives you the answer thing for it. You know, so if like a 6-year-old could figure it out, you know, probably not the securest thing in the world. You're probably not going to want your credit card set over the credit card number sent over the internet using ROT13. So we have much more advanced encryption algorithms now for that stuff.
That's what I was asking, like, how did they make that like even more advanced ones that?
Yeah, so the modern day encryption algorithms, they don't involve like adding some number to it. There's much more math to it. The RSA encryption algorithm, which is one of our more secure ones until quantum computing becomes a thing, is based on this thing that you take 2 very large prime numbers, you multiply them together. So now you have a giant number that was created from 2 large prime numbers. How do you get the 2 primes back out of it? That's a very difficult problem to solve, to factor 2 primes from a big value. You know, so the quantum computing example that you might find in textbooks is the idea of, let's say you take, you know, 2 different color paints, you mix them together, now you get a new color, right? How do you get those original colors back? Problematic, right? Not impossible. There's molecular things there. You could somehow magically pull it off, right? But very, very difficult. Quantum computing actually allows us to solve those problems pretty easily. But our normal classical computers where we're operating at these days, that's technically very difficult, even if you have a zillion computers working on it at the same time. So they're more based on like math tricks and stuff than, you know, us trying to be clever humans. Yeah, what's up?
I was